Okay, this is the 10th video in a series on single agent search. And in the last video, we were looking at weighted A star, and we were looking at the behavior of weighted A star. And what we saw is that weighted A star returned W suboptimal solutions, but we also found that weighted A star, that version of weighted A star, it required node re-expansions. And we saw that there was also some slack in the bound. And so maybe there was room that we could do better than weighted A star. So in this lecture, what we're going to do is we're going to look at a variety of other algorithms. We're going to look at the first thing, which is going to be focal list algorithms. And under focal list algorithms, we're going to look at A star epsilon and EES, explicit estimation search. We're not going to spend a lot of time going through all the details, but I'm going to give a high-level overview of how these algorithms work. And then we're going to look at an alternate approach, which is we'll look at improved optimistic search. Okay, so there's an original version of optimistic search and some enhancements that have been put on top of it. And then we're going to go ahead and look at a third algorithm, which is dynamic potential search. And these are all approaches that are trying to improve upon weighted A star, trying to take advantage of some of the properties we actually saw. And in fact, many of them will build on some parts of the proof that we saw in weighted A star. So if you remember in the proof of weighted A star, what we had is we had some node here, and we're going to call this F min, which was the node which was on the open list and had minimum F cost, and yet had not been expanded with that minimum F cost. And so we're going to be looking at this node and using this as a node that's going to help us to prove things. And particularly when we see this node along the path, on the path, the node with minimum F cost, that node is giving us, its F cost is giving us a bound on the actual solution quality. So if I was able to give us a bound, so if I know the F min in an open list, so this is in open, sorted by G plus H, so no W on here. If I keep track of this, it's basically what happens in an A star search, what the minimum F cost is, when it's, again, sorted in this way, then what I know is that this F cost is actually a bound on the optimal solution. So I know F min, because of the heuristic, is consistent, it's consistent, admissible, then I know F min has to be less than or equal to C star. And by extension from that, I know that W times F min must be less than or equal to W times C star. So if I'm trying to find a solution that is no more than W times C star, I can use as an estimate of that my F min. W times my minimum F cost gives me a bound on what the optimal solution cost can be. And so that's going to be a basis of a number of different algorithms that we're going to do. And in particular, we're going to start with this observation also that we had last time, which is that we really have two things that we're trying to do. We're trying to find the solution and prove the solution. And so by introducing a notion called a focal list, what we're going to allow us to do is we're going to use a focal list to guide our search towards the goal. And we're going to use a regular open list to be able to prove that we're within the bound. In particular, we're going to get, from F min, we're going to get our bound on the solution quality, but then we're going to guide our search using a focal list. So what is a focal list? The idea here is we're going to have so a focal list, again, in these algorithms where we assume we have we're going to assume we have an open list. And what we want to do is have a focal list, which is basically a greedy or greedier search. So we're going to prioritize states in the focal list by something more greedy than by the regular open list. And there's a number of ways we could define this, but if we let F min be the minimum F in open, then what we want the focal list to be, and a suboptimal bound of W, then the focal is going to be containing inside it any nodes that are in open, given that f of n of this n here is less than W times or less than or equal to W times F min. Okay. So F min tells us the actual bound on the solution, on the optimal solution cost. And we're going to say any nodes that are given F min are at most W times that, then those are going to be nodes that we could expand, but we could maybe expand them in a different order, trying to be more greedy in getting towards the goal. So the focal list is the nodes on the open list that have f of n, where f of n could be some other, so f of n is still going to be my g plus h, is less than W times the F min. That is, so that's the bound on the solution cost. But what I can do now, which is important, is we're going to be sorting focal by other measures. And we'll look at two examples of how that can happen, starting with A star epsilon. So A star epsilon is going to maintain two priority queues. It has open and focal. And what we're going to sort the focal by, now A star epsilon leaves it a little bit open, but if you look at the original paper, there's a few other details that aren't 100% clear from that original paper. But if we go back and we look at that, then what we see is that the focal list is going to be sorted by H of n, where this is maybe a commonly accepted interpretation of what A star epsilon should be doing. So we can have an open list, and the focal is basically running, greedy best first search, or pure heuristic search, whatever name you prefer there. But the idea is that we're going to say, look, I prefer just to go greedily towards the goal. I'm going to do that as long as I can. But what's going to happen is at some point I'm going to say, well, I've gone greedily for too far. And so now what I need to do is I need to go ahead and do some more proving of I need to basically raise F min so that I'm able to continue my search up. Okay. And so basically what A star epsilon does is it says, as long as there's basically states on this focal list so that are within the bound, then we're going to expand those states. And if we don't have any states there, then we're going to expand the states on open. Okay. And how does this look? There should be a link in the description below that will take you to a demo where you can run a bunch of different algorithms, including A star epsilon. A star epsilon, when you watch it, it won't be 100% clear what all the different pieces are going on there. So I'm just going to describe here really quickly what's going on. And anybody's welcome to go play with that demo a little bit later and do a lot of comparisons between the algorithms that are described here and other ones we'll be describing in the next videos. Okay, so the idea here is going to be something like this. We're going to start at the start state. And now it's important to note that nodes are going to actually be in two priority queues. We have basically our open list is running a regular A star search. And then what we're going to also have is we're going to have this greedy best first search. So here we go. The start, I'm going to expand it. And now once I have the F cost of the start, I'm going to be able to do some more node expansion. So what's going to happen here is I'm going to do some sort of greedy search. I'm just going to go off and expand some number of nodes. And so this is, as I said, it's a greedy search. But at some point, what's going to happen here is we're going to have some number of nodes that are being generated here that are on the edge of this frontier. Okay, so we searched all the way to the end here, and then we generated a bunch of states here that are more than W times C star, or W times F min suboptimal. That is, we're no longer allowed to expand these states any longer. So what happens here is just, I'm going to draw this in two places, is we're going to have essentially our open list is going to have all of these states here, which is every state we've generated. And then we have but the number of nodes that I've expanded in here is actually going to be relatively small. So I've expanded some number of nodes near the start. But I've actually generated all these states here, and I've even generated up to these expensive states here. They've gotten too expensive to go on to the focal list, which is this list here, but they're still on the open list with large cost. And then, so the focal list here is basically going to run out of states that it needs to expand. But it's got these, states out here that it wants to expand. And now what's going to happen is it has to go and expand the open list. And so what we're going to do is we're going to go back into the open list here, and we're going to start to expand states so that I can decrease the fmin. And in that expansion process, what's going to happen is that, just to show it here, is that all of these states have actually been expanded by the focal list already. And now A star epsilon is going to come to these states, and it's going to find, it's going to find paths to them, which might be better than the previous paths. So they're going on to the open, raising up fmin, and they're going to be expanded. We're basically doing a regular A star search here. But what that's doing is it's going to repopulate. These states are going to be repopulated back onto the focal list here. And then once I've done that, I'm actually now able to re-expand the focal list. So the focal list is going to go down here, and we may actually get out to expand these states that we couldn't expand before. But eventually we're going to hit the limit. We're going to come back to the A star search. We're going to have to expand these states out here. And then we're going to have to repopulate those into the focal list. And then the focal list is going to re-expand them there and continue outward. So what happens in A star epsilon is that we basically push out really greedily. We hit our limit. Then we go back to the beginning of the open list from our focal list. We expand the open list out a little bit. Those states now go back into the focal list, and then they get pushed all the way along on the focal list. And we'll continue this process of expanding and re-expanding states from open and focal. And so this is a really good idea in the sense that we want to separate the notion of the focal list, which is trying to guide the search to say, let's search in the direction of trying to find the goal as quickly as possible, and then an open list, which is trying to prove the quality of the solution of the goal. So that's really good. But the actual behavior that you get here in many domains, especially domains where I might be finding shorter solutions, means that we might do a lot of iterations going around here, basically going around and around, finding slightly shorter solutions, updating our focal. In particular, we're pushing all the way until we find very suboptimal solutions here, or states that we are very far from being able to prove that they're in the suboptimality bound. And so that's going to get a little bit expensive. So A star epsilon was a really nice idea that introduced this idea of a focal list, but has not been a particularly successful algorithm. Now, there's an algorithm here, which I'm just going to spend a short amount of time on because it's somewhat complex, but it's sort of like it's going to take us sort of to the maximum that we can possibly do here in terms of trying to get the best behavior out of something like a focal list. And so EES stands for Explicit Estimation Search. And what it's actually going to have is it's going to have two focal lists. So focal D, which is going to be thinking about the goal. We're going to have focal F. And then we're also going to have the open list here. Okay. So focal D is basically going to try and do this. It's going to try and minimize the number of steps to get to the goal. Focal F is actually going to try and minimize the distance to the goal. And then open is just a regular open. Okay. And so what EES is saying is, look, when I'm doing my search, I don't just want to think about the cost to the goal. If I can get to the goal in fewer steps, then I'm going to do fewer node expansions and I'm going to get better performance. So it asks you to provide an estimate, which is the estimate of the number of steps it's going to take to the goal. And this is really in a domain where you have unit edge costs, then we don't have this sort of estimate. But in domains where we don't have unit edge costs, then this is something like some sort of heuristic that's modified to be a unit cost. So for instance, in grid pathfinding, where we might have diagonal edges and cardinal edges, and so we might do diagonal edges times the square root of 2 plus cardinal edges times 1. We could also treat our diagonal edges as having cost 1 instead of square root of 2. And so that would give us an estimate of the number of steps that we have to go to the goal versus the cost. In other domains, we might have sort of very expensive cost functions based on like how heavy something is, or like if a vacuum cleaner robot, depending on how much dirt is picked up, it gets heavier and then maybe it costs more to move. And so we might have that as part of our heuristic. But if we want to think about the number of steps to get to the goal, then we would ignore the cost of moving that robot. And we just think about, well, how many steps is it going to take it to get back, no matter the cost of those steps. And the F cost is, what this is using is it's basically using something like greedy best first search that we were using inside here, but it's going to use some sort of estimate that's trying to get us to the goal as quickly as possible. And we're not worrying about staying within the bound. The heuristic that's being used in particular here to guide it, we might be using a heuristic with a higher weight than we actually want, or we might learn some other heuristic. Basically, we can use any estimate or any priority function here that we want that's going to try and guide us to the goal. And then what we're going to do is we're going to use the open list and this idea of fmin similarly to try to bound our performance. So basically, EES is 3 steps, and there's a few more details here, but basically it's going to be try the best focal D. That is the state with the minimum distance in terms of number of steps, sorry, not distance, but the number of steps that I need to take to get to the goal. If that node is within the bound, so we're always going to make sure we're within the bound, then I expand that state. If that's not within the bound, then I'm going to try the best focal F. So now we're just going to use some sort of greedy estimate to get me to the goal as quickly as possible. And if I can't do that, then I'm going to try the best F, which is just a regular F cost. And so again, when I say try here, what this means is we look at the fmin that we had previously, and I have to be within W times fmin. Okay, so if whatever this node is that I'm trying to greedily prioritize in terms of getting to the goal, if that state's F cost is less than or equal to W times fmin, then I can expand it. If it's not, then I'm going to try the best focal F. If not, I'm just going to try the best F cost, which of course, this will be fmin here. So this is what's going to increase fmin and allow us to continue to search here. What we notice in both of these approaches, A star epsilon and EES, is that we are explicitly maintaining the open list. And so therefore on the open list, we're explicitly having fmin. We maintain that as a separate state. And with fmin, we're also keeping the absolute minimum. Like this gives us the proof that we are within the W suboptimal solution. And so that's important because that's what they're using for maintaining. In fact, for both A star epsilon and EES, both of these problems, they prove that each expansion is bounded. So I'm not allowed to expand a state until I prove that that node is within the limit of expansions that I'm allowed to do. I prove that that node is W suboptimal, and then I'm allowed to go ahead and expand it. But in order to maintain both of these algorithms, I have to keep this open list with sorted by F cost, and I have to keep increasing this minimum cost. And that actually requires that I'm going to be continually expanding states from this minimum open list here to try and push forward to try and be able to push forward the bound of states that I'm able to expand. Okay, so EES has been shown to be on weighted domains where we have a broad range of weighted costs and on domains where we do not have a lot of cycles in them, the EES has very, very good performance. But that is a subset of all domains. And so we're going to go forward and look at a couple other algorithms that have been proposed and how those work. Okay, so these are our explicit focal list algorithms. We're now going to look at two other algorithms here. And so first we're going to look at improved optimistic search. And so, of course, I should explain what optimistic search is, but the improved version is actually quite a bit simpler than the original version. And at a high level, they're very similar, but there's some of these low-level details about doing state re-expansions and things like this that I don't want to get into all of those details. You can go back to the original paper and find these. So let's go ahead and look at improved optimistic search and see what we can do with this. Okay, so the idea here is that in EES and A star epsilon, we proved that every expansion was bounded every time we did an expansion, we knew that we were within the bound, and if that was the goal, we'd be able to immediately terminate and know that we had found a W suboptimal solution. And what we're going to do here is actually we're going to do something a little bit simpler by maintaining the data structures and things that EES had. Is we're basically going to have two searches. So one, we're going to have a suboptimal search. And this is basically going to be more greedy than W suboptimal. Okay, so I might, for instance, a common thing here, instead of using a weight of W, I would say use a weight of 2W minus 1. And essentially what 2W minus 1 is if you look at what's going on here. So if I have a W of 1.5, that means I'm allowed to be 50% suboptimal. 2W minus 1 gives me an optimality bound of 2. And so what I've done is I've taken the suboptimal portion and I've doubled it. So I'm allowing basically to be double the suboptimality I previously was allowed. Okay, and when I use, I'm going to use something like this, and what I'm gambling on a little bit is that I'm going to search to the goal, I'm going to use a higher suboptimality bound, but I'm still going to find a solution which is actually W suboptimal. And this comes from the fact of the proofs that we were looking at in the last video, that weighted A star in most cases is actually going to find much better solutions because the proofs actually have a lot of slack, especially once our search goes, we go farther into the search. So we're going to do the suboptimal search, and we're basically going to search to the goal. So we found the goal, we found a solution, and we've done it in the greedy way. And then what we're going to do is we're going to use an A star search to prove the suboptimality. Okay, this is a little bit easier because now we don't worry about nodes going back and forth between open and focal and then back to open and then going back to focal. We're going to do all of our search. We get to the very end of the search, and now we're going to do an A star to try and prove our solution. And so immediately from our A star search, we're going to get an F min. And we're going to say, if we're within W times F min, then we know we can, then we've F min. So if I find a solution, let's just say here, I found a solution of the found solution is 100. And then I look at F min is, let's say F min is equal to 50. And if W is equal to 2, then I immediately would say, so just if I think about the F cost, the regular F cost of the start state, if it's 50 and W's 2, I found a solution of cost 100, then hey, I'm already proven that I'm within the 2 times bound, and I'd be able to immediately stop the search. And I wouldn't need to do any interleaving or other things like that. Now, why would this matter? If we were to actually look here at F cost, so this is over time, and this is F cost of nodes that are expanded. What we actually see is that over time, the F cost goes up and down until we eventually get here. Sorry, I should, not down here, but So it's going to up and down, and then I get to the goal. So what actually happens is that when I find the goal here, I might have expanded states with f costs that were higher than the goal. And then it comes back down and I get to the goal. And what that means is that if I try to prove every expansion when I do it, I might have to do a lot of work to prove that this node is W suboptimal, but I'm actually going to find a goal down here with lower f cost, and it'll actually be easier to prove that state is W suboptimal than it will be to prove every state along the path. So that's one reason that we might want to actually find an entire path before we try and do the proof. There's another thing that we can do is that we can use some things about the f cost that we do expand to improve the solution bound. So if we think about the maximum f cost that we do expand, then this actually gives us a bound. So let's just say this was 150, and we know that our weight is equal to 2. Then what we know is, then we know that C star has to be greater than or equal to 75. Okay, because we expanded a node with 150, or whatever weight we happen to use. If we're using a weight of 2, then I know the solution had to be 175. And now if my actual bound I'm looking for is 1.5, so that's 75, then, or let's say that my bound is 1.333 to make this a little bit easier, then this would actually say that a solution of 100 would be within that bound. Okay, so we have, so by basically ignoring the bound as I do the search, waiting till I get to the goal, I get this additional information through the search that may make it easier to prove that the goal is bounded, that I have found a bounded cost here, based on both the maximum f cost I've expanded during the search, and also just based on the fact that the goal could have lower f cost, so that it may be easier to prove even looking at the start state. There's one other thing that we're able to do here as well that that isn't done quite as easily. So imagine that I've got my greedy search here, and I find some path to the goal. So there's that path, and this is my suboptimal path. And then what I'm going to do is I'm going to do my A star search. Okay. When I complete this search, I can actually go back into this path, and I can mark out, here's the path that I found to the goal. And when I start my A star search, what I can do here is in my A star search, I may actually find, so I'm doing an A star search where all I'm trying to do is raise F min to be large enough to prove that my solution is within the bound. But at the same time, I might actually find a shortcut on the path that was discovered by the original search. And if I do that, then I actually can lower the cost of the solution that I found, therefore making it easier to prove that I'm actually within the bound. And then in general, even if this bound might have been above my suboptimality bound that I was allowed, I might be able to start improving that path, and therefore make that this solution easier and easier to prove, so I could bring it in to be within the bound by updating it. Okay, so improved optimistic search is this next algorithm here. And what improved optimistic search is doing is it's going to search all the way until I find the goal, and then it's going to try and prove it. And by doing that separately, it gets some nice advantages in terms of making making it a little bit easier to prove the solution that I do find. Okay. Now, this algorithm is still going to require 2 searches, because we still have our greedy search and we still have our A star search. There's some interactions here. Things are a little bit more complicated, but this is still a pretty simple algorithm and can get pretty good performance in practice. And so the last algorithm we're going to look at to complete this portion of the lecture is now going to be something called dynamic potential search. And just to say one more thing, all of these algorithms have required re-expansions. As I come inside here, this A star search is re-expanding states that were already expanded in the greedy search. And so this is not doing it as bad as we might see up here in these algorithms. And we're going to look in dynamic potential search. Dynamic potential search is also going to have to do node re-expansions. But dynamic potential search, well, and again, it's a really interesting algorithm that can have really good performance. And so we'll look at this, and then we'll look at the drawbacks. And then in the next video, we'll start getting into, well, what are the conditions that are required to avoid these re-expansions, and how bad can re-expansions actually be in practice? Okay, so dynamic potential search says, we care about this fmin because fmin is what we use for proving states. But what we're going to do is, instead of thinking about just sort of running a search, is we're going to think about how much potential a state has to get to the goal within the suboptimality bound, and we're going to prioritize states by the potential they have versus some other measure. Okay, so dynamic potential search is going to look at states with a priority, and again, this is going to be a best first search based on these priorities. So it's going to use a priority of W times Fmin minus G of n over H of n. And let's talk about what's going on here to understand this. So the first thing we see is that Fmin is this lower bound on the optimal solution cost. Okay, so we're going to maintain this lower bound. And that means that what we're going to have to do is we're going to have to re-expand states so that I know, we'll prove in the same way in the last video I proved for weighted A star, that when we re-expand states, they will always have the minimum estimate for, the F cost. And then I know basically there's going to be a node on, to be more precise, there'll be a node on the optimal path from the start to the goal that will have, there will be a node there that is on open list with the optimal cost. And so we know that there will be a node on the open list, which gives us a bound on the actual optimal cost to reach the goal. And we can multiply that by W to get a bound on the optimal cost of, to get the W bound on the optimal cost, or the solution costs that I'm able to find. And so that's what we're getting here when we multiply this by W. So W times Fmin basically is giving us the suboptimality bound. Okay, so these pieces here taken together are the suboptimality bound. So that's the maximum suboptimal solution that I can find given the search that I have so far. The next piece that we see here as part of this is we look at G of n here. And so what G of n basically is saying is, this is how much have we used of our suboptimality. How much of the path cost is used already. And so when we subtract these two overall, we have the absolute value of how much suboptimality we can use in the remaining portion of the path to find the path to the goal. So looking at this whole thing, what this is the remaining suboptimality. Okay, so if the minimum F cost is 50, I know that the optimal solution has to be greater than 50. I'm looking for a bound of 2, so that would say that I could find a solution of up to 100 at this point, and I would know I'd be bounded. And then I know that I'm on some path, and maybe that path has cost 50. So that would say, well, here's 100 minus 50. I have 50 length left in the path that would still allow me to be W suboptimal. And then H is our estimate of what the actual, what is our estimate of the cost that I have to use to get to the goal. So it's just cost to go. And so what's happening here is we're looking at how much suboptimality we have, just to highlight this up here. So this is the suboptimality that I have remaining divided by the cost I have to go. Okay, so this is a measurement of potential. If I have 100 suboptimality remaining and my heuristic says I'm going to have to use 100 to get to the goal minimum, then I've got this very low priority. I'd have a priority of 1. But if my priority says I have 100 to get to the goal And this path only was going to take at least 10. It may take more than that. It's going to take at least 10 though. Then I actually can go 10 times longer than that and actually still be within my suboptimality bound. So this is looking at the potential that is remaining to get to the goal and saying, let's expand states in the order of their potential. Okay, and so that's what dynamic potential search does. And it must re-expand states whenever it finds a shorter path. But other than that, it's able to do this using one priority queue that's sorted in this way. Now there's one drawback here. And that is that fmin is not constant, but fmin changes during the search. So what happens? I expand a bunch of states, fmin goes up. When fmin goes up, the priority of every single state in the open list goes up. And therefore, I now have to resort my open list because the priority of every state changed according to fmin. Okay. But this algorithm then, if you think about when I get to the goal, like when my heuristic gets to 0, basically I get an infinite priority. So I'm always going to do the 0 cost heuristics first, but very low heuristics are going to have very high priority. And states that are farther away from the goal are going to have lower priority, or that have less potential to reach the goal within their suboptimality bound. And if you go ahead and actually look at the demo, if you get a chance to look at the demo, in the demo, and this is a great observation by the authors of this paper. So what we're going to do is we're going to write here a state. We're going to plot every state. This x-axis is going to be the h cost of the state. The y-axis is the g cost of a state. And we can think about for every state that is in the state space, it has an h cost and a g cost when it's discovered in the search. And so that's, these are, we could imagine plotting these in a plot. And what it ends up is that if we do something like weighted A star, so there you go, weighted A star is equivalent to drawing a diagonal line through the space like this. And we just take this line and we move it through the state space according to the slope. And then whenever we come to a state here, we expand that state until we get to the goal. And what dynamic potential, so it's moving the whole line across. So the line would start here and then the line would move up to there. What dynamic potential search is doing is it says, well, right here, this is W times fmin. And that's the current bound that I have on my cost. And what I'm going to do is take W times fmin, and we're going to plot this down here. Actually, let me do it in another color just to make this a little bit clearer. So we take W times fmin, and we're going to draw that line there. Can even make that a little bit thicker to make it clear. Okay, so that's a W times fmin line. And what we're actually going to do is we're going to rotate this line. Now, in practice, the slope here actually never gets steeper than the W's or shallower than the W slope here. But what we're actually going to do is we're going to rotate this line through the state space. So later on, I might actually be searching with something that looked like this, depending on what my W is. But the idea is we're going to rotate this. And what happens is these states here have high potential. So these are states with high potential, and these are states with lower potential. And so we're sweeping through the state space, not taking a fixed line and drawing it across this way, which is what weighted A star does, but it actually takes a line and goes through this direction. And in sweeping through the state space in that way, that's what is actually happening to the priorities. It's a little bit hard for me to draw this here, but if you go to the live demo, so during the links below, then you can run weighted A star. You can watch it sweep in the visualization. You can watch it sweep this line through the state space. You can watch dynamic potential search be rotating this line through the state space as it's trying to expand states. But this is really an interesting idea that is basically saying, look, we want to look at this ratio of the remaining suboptimality to the cost to go, which is basically how much potential we have to find a solution. This gets rid of the multiple priority queues, so that's really nice. But what it doesn't do is it doesn't get rid of node re-expansions. And again, if you watch this demo, particularly on the state space, this grid-based state space that's being used in the demos, you'll see that dynamic potential search has to do a lot of node re-expansions. And so in the next lectures, what we're going to be looking at is what is the cost of node re-expansions and how can we design algorithms that avoid node re-expansions when finding suboptimal searches.